School in Edinburgh. They're hoping it'll be a hit because they're planning to give any profits from record sales to the United Nations Refugee Fund. Louise Batchelor reports.
If it is, will someone tell us so?
Though the pop world's a fickle one, the choristers, with soloist Susan Hamilton, certainly appear to have the ingredients for success. They look the part for a Christmas time hit, the tune's catchy and the message strong. Their children's song for peace is a plea for reassurance about the future. It could be dismissed as trite, except that the choristers themselves strongly believe in what they're singing, and the man who wrote it, a builder called George Cochrane, was inspired to do so by his own children.
There's been quite a lot of songs written, about peace and what's happening in the world, but nothing from kids. So I actually wrote it as if it was a child asking the question, and the first thing that came to mind was "tell us." And also I thought, is it worthwhile dreaming, and so on, and that's where it all came from.
The union which represents safety workers in Britain's mines, known as NACODs, has decided not to go on strike tomorrow after all. NACOD workers make sure the coal mines are safe, and the strike they'd planned to begin tomorrow would have closed all the pits in the country, even those where some miners are still working. The strike was called off by the union after successful talks with the National Coal Board and the peacemaking body ACAS. And finally tonight, a pottery firm in Stoke-on-Trent has had a smashing time today. The Ainsley China Company, who makes small china animals, are fed up with manufacturers in the Far East copying their designs. So today they dealt them a crushing blow, as Gary Hudson reports.
At first glance, there's not much difference between these two sets of animal figurines. In fact, the ones on the left are cheap copies made in Taiwan and selling for half the price of the originals. The Far Eastern manufacturers, who've probably never even seen a badger, simply copy the British craftsman's work, and it's costing British industry tens of millions of pounds. But Ainsley China won possession of hundreds of the fakes in a court case and decided to crush the opposition quite literally with a road roller. The company bosses had a smashing time as they struck their blows for British industry. The fake animals would have sold for £10,000 if they'd been real. Now they look like the result of a bull in a china shop.
And that's all for tonight. We'll be back again round about the same time tomorrow. Until then, bye-bye.
There's adventure tomorrow afternoon at 4:30 when that mighty monster Godzilla is summoned to help the crew of the Calico when they discover a submarine frozen in time.
He mustn't damage the submarine. It may be a very important find. Carl, what's that underneath the sub?
It looks like a torpedo. It's much bigger than the ones they used in World War I.
Perhaps this sub was on some kind of special mission.
On Blue Peter at 5 o'clock, Simon takes Michael to his dad's farm in Derbyshire, where 300 sheep are in for a shock. They're all going to be given a cold bath. It's for their own good, but sometimes they need a bit of gentle persuasion. Michael has his work cut out, coping with the unwilling ewes, rams and lambs, under the watchful eye of the law. Join us tomorrow afternoon on BBC-1.
And this is BBC-1 with Johnny Ball and Think of a Number.
And now it's welcome to the All-Star Think of a Number show. And here is your genial host, Johnny Ball!
Hello, welcome to the All-Star Think of a Number. When I say All-Star, I mean All-Star. The Spandau Ballet Culture Club
few of the stars who will not be appearing tonight. Not that kind of stars. This program is about the kind of stars you see through a telescope. Oh, hit me on the head. Oh, telescopes make things bigger. My head's swelling up already. Telescopes also make things look closer. Get back, get back. Oh, you there, give me a number between 1 and 10. 5. Now, I heard you say 5, but through here, it looks like you're saying 10. If I look through the other end, it does. If I look through the other end, it would look like you're saying 2.5, because that's what telescopes do. They enlarge things, and the program is about telescopes and stars, the whole field of astronomy. And you know, astronomy goes back a long, long way. It's the oldest science, and at one time, it could be very dangerous being an astronomer. Time ago, in year 2126 BC, Chinese emperor is sitting outside palace with servants and cohorts all around having picnic, possibly English takeaway. Suddenly, invisible dragon appear from nowhere and begin to devour the sun. Immediately, Emperor and all his people make great noise, banging on drums and drums and shouting, driving away the dragon. Shoot it up! It worked! And dragon cough up sun and disappear forever. Immediately, everyone at peace once more. But Emperor send for astronomers named Sai and Ho. Sai, say Emperor, you know foretell of coming of dragon to eat sun. Ah, they say, foolish Emperor, it's not dragon, it eclipse of the sun. Me foolish, you foolish for not telling me, say Emperor, and draw sword, and with 2 swipes, Sai becomes so high, and Lo becomes so low. End of story. That's all. So you see, being an astronomer, well, it could be a very dangerous job, but the early astronomers were actually very, very good at their job. They helped people to understand the length of the year, for instance, and when the seasons occurred. They also helped travelers, because the astronomers told them which stars to look for, what patterns in the sky, to guide them on their way. So astronomy was a study of the sky to help people on Earth. Studying the stars for themselves only really got going with the advent of the lens. Now, you can make a lens for yourself very easily. All you need is a bottle full of water, right? And it's amazing what a lens will do. I've got a card here with an arrow on. Look what happens when it goes behind the bottle. The arrow turns the other way, because the lens bends the rays of light. That's what a lens does. Now, this simple lens bends the rays of light and switches left to right and right to left. With a round lens, you could actually switch things from left to right and right to left, and also from top to bottom. Can you come and put your little face there? Just peer through the lens there, this round bottle. And now, at the moment, you're very blurred. But if I pull the lens away, we should be able to see your head upside down, or back to front. Because the lens is reversing, bending all the rays, so the whole image is reversed. And it works very like the eyeball. Thanks very much for the loan of your head. It works very like the eyeball, because the eyeball's round, and the lens at the front is curved as well. Now, the first person to suggest lenses would help people with poor eyesight was a man called Roger Bacon, who was a friar. Well, you'd expect him to be a friar with a name like Bacon. However, that was in the 13th century, and it was a couple of hundred years later that a spectacle maker called Lippershey found that if you look through 2 lenses in line, the church steeple some distance away seemed much nearer. And you got some of these, so put them in line. The smaller one near your eye, and the other one further away. Is it working? Yes. Great! You've got a telescope. Now, Isaac Newton did a lot of experiments with lenses and with prisms, and he found that when you bend light through a lens, it tends to split it up, and you don't always get a very good image. He said, if you're going to make a good telescope, don't use lenses, use mirrors. You can get some amazing effects with a couple of mirrors. Look at that. There's what, 3 of me? There's 4 of me. There's 5 of me. And there's about 6. But you'll notice, if you look at all the reflections, that the real me is quite bright and the others get dimmer. Of course, I'm breathing on the glass. But that's because with every reflection, you lose a little light. But that didn't worry Newton, because he was only going to use 2 mirrors. But one of them had to be curved. And there's curved mirrors everywhere. Spoons reflect very well. What you need to do is lick the soup off first, so it's nice and clean. And if you look at the back, you get a bigger nose and your ears disappear. But look inside the spoon, and you'll see you're upside down. You've got a bigger curved mirror here. And it's a big curved mirror that gives you a very good telescope. Every curved mirror's got a focal point. And I'll see if I can find the focal point with this torch. And watch what happens when I pull the torch away. When I get to the focal point, you see nothing but light. A whiteout. Because every ray of light is reflected back to the source. Or, as the telescope works, all the rays of light coming in are reflected to one point, the focal point. This apparatus shows how a telescope works, okay? Now, what we've got is 2 rays of light and a curved mirror. It's a sort of cutaway of a telescope. As the rays of light come in, they bounce to this mirror here. Can you see them? There's one down here, and that also bounces to this mirror at the focal point. In big telescopes, the observer sits at that point and sees all the light as it's gathered by the telescope. But in this case, it's reflected down here and comes out at the eyepiece here. But whether you use refractor telescopes with lenses or reflector telescopes with mirrors, once the telescope had been invented, it opened a whole new field of astronomic discovery. Now this is a model of Galileo's first refractor telescope, using lenses, and with this he made these drawings of the moon, the first accurate maps of the moon. He also looked at lots of other heavenly bodies, and he looked at the sun. Great mistake, never ever look at the sun through a lens, because poor old Galileo went blind through doing just that. In the year he died, Isaac Newton was born, and this is Isaac Newton's telescope, or a model of it. The mirror was at this end, the light came in here, and then was reflected back to the focal point here and out to the eyepiece. And they both made tremendous discoveries. But the man who really began to understand the dimensions of our solar system, that was a man called Johannes Kepler. This is an orrery, a model of our solar system, with the sun in the middle and all the planets revolving round in their places. Now, it's very old. This one was made, we think, in 1812. And it's not an accurate model. If this was accurate and to scale, the Earth would be so small at this distance from the sun that you really wouldn't see anything at all. It'd be a minute dot. But it was Kepler who worked out the first dimensions, the accurate dimensions of our solar system. Because he worked out that the speed at which a planet travels around the sun gives you an idea as to how far away from the sun it is. Where's my ball? Thank you very much. You can prove this with a ball on a string, right? And I've got this one through a tube so I can lengthen my string. Now, if I swing it round on a long string, you can see how long it's taking to go around. if I shorten the string, it goes much faster. So Kepler was right. And by working out how long it took the planets to go around the sun, he could work out how far from the sun they were. But he found, from the figures he had to go on, that the planets didn't seem to move at a regular pace. They seemed to be going at one speed and then speed up for a while and then slow down again, only slightly. But these discrepancies were there. And he realized that must be because the planet wasn't going around in a circle, it was going around in an egg shape, an off-shaped circle, an ellipse. And you can see what happens when a ball goes round in an ellipse by shortening the string. It's going quite slow, and as you shorten the string, it goes quicker. And that's what happens to a planet going round in an ellipse. This is much exaggerated. But using this information, Kepler was able to work out the accurate distances from the planets to the sun, and from any planet to any other planet at any given time. So after Kepler, we understood our solar system. But what about measuring the distances to the stars? A vastly different problem. The ancients thought all the stars were stuck on the inside of a big dome. The sky was this dome, a great distance away with all the stars stuck on it, all the same distance away. This could be, if you like, a piece of the dome with the stars stuck there. But astronomers noticed that some stars appeared to move in relation to other stars over a period of time. That's a period of a year. And they thought those stars were perhaps nearer. So perhaps they could measure the distance. Who'll come out and help? Got a pencil there. What I want you to do is look through here and look past the star to the Earth and line up the Earth with the star and make a little cross. Okay? Now let's assume this is the Earth in midsummer. This is revolving around the sun. Right? In midsummer, that star would appear to be with the other stars in that position. But as the Earth moved round, the stars seemed to move. After a few weeks, it was there. Can you mark the new position? And join them up with a line. That's it. And now, as the Earth goes round, try and make a continuous line. Keep it lined up. As the Earth moves round, midsummer to autumn. Very good. From autumn to October, November, December, midwinter. And from December through to January, New Year, February, March. From spring, in April, May, June, and back to midsummer. That's how long. That's terrific. Give him a round of applause. That's marvelous. Very good. So you see what we've got? We've got the path that the star appears to travel along over a period of a year. In midsummer, the star appears to be to the left of the heavens over there. But in midwinter, when they look at the same star, it seems to have moved. It seems to be over to the right. The reason being because we're looking at it at different times of the year from a different angle. Now, if we can use these angles, we can form a triangle. We know that the Earth is 93 million miles away from the sun. So from there to there is 2 93s, or 186 million miles, the base for our triangle. And by measuring accurately these angles, it was possible to form a triangle and work out the dimensions of the triangle, and thereby work out the distance from the star to the Earth. The first star to be measured in this way was Cygnus, which was found to be 60 million miles away from Earth. 11 light years away. That's a very near star. The furthest object we can see is Andromeda. And that's not 11 light years away, it's 2.2 million light years away. So you see, all the stars are all different, vast distances away from the Earth. But we tend to think of them all the same distance away. And we identify the stars by the patterns they make in the sky. This is a pattern of stars that everybody can identify, or just about everybody. It's called the plough. And you can recognize it by its distinctive shape. And we all think that all these stars are the same distance away from Earth, but nothing could be further from the truth. This one is 55 light years away. This one, 200 light years away. And from anywhere else in space, you just wouldn't see the same pattern at all. It's only from Earth that we can identify this pattern of the plough. And in our lifetime, the stars don't change position. Not apparently, and so we can make very accurate star maps. Now, the trouble with star maps is they tend to be a bit big. And when you're going out stargazing, you have to go out on a dark night. And if you're out on a dark night and the wind's blowing and you're messing around with a map, it can be very troublesome indeed. So a good idea is to find a star map and identify the particular stars you want to see in the heavens and get some tracing paper. And trace the pattern out. There's the plough traced out. And then transfer that to a piece of black card and prick holes in it. And then you've got a holy card. And you go out with your lamp or your torch and shine it through the card. And there's your star formation. And then you can compare it with the patterns in the sky and identify any particular star you like. You can make all kinds of different maps. The kids have got some more. That's Orion. That one's Cygnus. And that's Ursa Minor. Once you get hooked on stargazing, you feel you want to get closer to the stars. And it's no good climbing on your dustbin because you don't get that much closer. What you need is a closer look through a telescope. And this is the kind of telescope you might buy if you're an astronomical beginner. But it still costs quite a bit. It costs about the same price as a bike, about £100. But it magnifies by 100 times. So it's a very good telescope. You've got a small telescope here, helps you to line up in the general direction, and then you've got your eyepiece here. This is lenses. It's a refractory telescope. Okay? And you can adjust it very carefully. And you get some pretty good views through a telescope like this. But if you really get the bug, you might invest in something like this. Because some amateurs use telescopes this big. It costs you, about £1,400, that's all. But it's a very, very good telescope. It's also got an equatorial mount. What's that? Well, this bit here is parallel to the polar axis. The result is, as the Earth turns round over 24 hours, the telescope turns the other way over a period of 24 hours. And it means that the telescope is always pointing to precisely the same point in the sky. Now, it's a reflector telescope. The light comes in at that end, the mirror's down here somewhere, and focuses the light to the focal point up here. And it comes out to the eyepiece here. And because it's always pointing at the same place, you can actually lock a camera on there and take a very long exposure, lasting all night, to get a very precise picture of an object in space. What else is there to see in space besides stars that don't move? You can look at comets. Because there's thousands of them, you know. Some comets return quite regularly. One comes back every 3 years or so. One seen in 1914 won't be back for another 24 million years. But the most popular comet of all is Halley's comet. Right. Halley's comet appears about every 77 years. And you can trace back in history the years when it appeared. For instance, it appeared in 1066. This is part of the Bayeux tapestry, depicting that year. There's the comet. And it was said by the Normans to be a very bad omen for Harold. And sure enough, he got shot in the eye with a Harold. It also appeared in 1301. And this picture of the Nativity was painted in 1303. And there's the Star of Bethlehem, which is a comet. Obviously, the artist was inspired by Halley's comet and put it in his picture. The artist's name was Giotto, and the space probe going up in 1986 to look at Halley's comet is also called Giotto. We'll understand from this probe a lot more about comets. We know that the nucleus is made of clumps of ice. We know that the tail is very, very thin gas. And after that space probe, we'll know a lot more. But the most exciting thing that's going to happen in space is when they put into space the Space Telescope. It's hoped that the Space Telescope will go into orbit in 1985. Its mirror will be 94 inches in diameter, which is only half the size of the mirror in the telescope on Mount Palomar. But it'll see much, much more, because viewing space from the surface of the Earth is rather like lying on the bottom of a muddy pool looking up. So much of what we might see in the heavens is blocked out by our atmosphere. We need the atmosphere to protect us from the radiation from the sun. Too much of that and we'd fry. But we can't see clearly into space. With this up in space, there'll be nothing blocking the view. It'll see 20, perhaps 50 times as clear as any telescope has ever seen before. And we should learn so much more about space. So every amateur and professional astronomer is just waiting for it to be in position. If you like, they're all watching this space. Let's have a trick. What we've got here is the signs of the zodiac. Astronomy is studying the stars. Astrology is reading meaning into the movements of the planets and how they affect us. So here are the astrological signs. Do you know your birth sign? Don't tell me it. Do you know it? Can you spot it there? Right. We've given them all numbers, right? Here's some cards, and all I want you to do is select that number of cards from the top of the pack and place them underneath the pack. And tell me when you've done it. You've done it. Right. Take the cards. I don't want them. Right. And now what I want you to do is deal them out. Deal one on 12 and deal them around the clock. Right. One on each number. One corresponding to each sign. I'm a Gemini, the cricket. Oh no, it's not. That's Jiminy, isn't it? Yeah. Anyway, I don't know which one yours is. Would you like to touch it? The card corresponding to you. Oh, you're a Taurus. You were born on the Taurus the bull. Right. Now, I'm going to turn over all the rest of the cards. And they're all just odd cards from the pack. But yours is amazingly special. There we are. You're a lucky star. It's a trick. Of course it's a trick. If you'd like to know how to do the trick or anything about telescopes or lenses or star maps or astronomy, drop us a line. But remember this, as an amateur astronomer, you've just as much chance of discovering something new as the professionals. You might see something the professionals have missed, so keep looking up. You might see stars nobody's ever seen before. Oh! Bye!
BBC-1 presents a new series for the new season, I've Got a Secret, with a variety of guest panellists, hosted by Tom O'Connor.
Right, it sounds like you took your clothes off. Did you take your clothes off and wave them around to alert somebody some danger?
Did you take them off yourself, or was it an accident?
I took them off myself.
Why? A new series, I've Got a Secret, starting tonight at 6:55 on BBC-1.
And it's comedy now on BBC-1 as we join Richard Bryars and Felicity Kendall as Tom and Barbara, intent on enjoying the good life.